What if love was infinite? What if there was always the perfect match for everyone, no matter how many people exist? Today we're going to explore how mathematicians think about infinite matchings using bijections through the lens of dating, marriage, and hookups. Imagine you're the town's top matchmaker. Your job? Pair up all of the male and female cats so that everyone gets a partner. No lonely kitties allowed. But this isn't just about throwing random cats together. We need perfect pairings based on strict matchmaking rules. To understand these matchmaking rules, we need to redefine our job a bit. Let's consider two sets, one containing all of the male cats, and another containing all of the female cats. Then we can consider a matchmaking function where you input a male cat and you get out the corresponding female cat partner. To get everything to work properly, this matchmaking function needs to satisfy two properties. The first property is that the function is injective, which is also called one-to-one. This means that every cat gets exactly one match, so no double booking, no love triangles, and no confusion. For example, if this function is not one-to-one, it would mean that Luna the female cat gets paired with both Mittens and Whiskers. But if the function is one-to-one, it means that Luna gets paired only with Mittens, a clear one-to-one match. The second property is that the function is surjective, or in other words, that the function is onto. This means that every cat must be matched, no lonely hearts left behind. For example, if this function was not onto, it means that there would be female cats who did not have a match. And if you have a matchmaking function that is both injective and surjective, i.e. both one-to-one and onto, then the function is called bijective. It's like the mathematical version of Tinder, but without the ghosting. Now the question is, can you always find pairings between male and female cats that always work like this? It should be clear that if you are considering a finite number of cats, then for the matchmaking function to be bijective, you need to have the same number of male cats as female cats. If there are more male cats than female cats, then the function is not injective, i.e. one-to-one, since there will be female cats that have more than one male partner. If there are more female cats than male cats, then the function is not surjective, i.e. onto, since there will be female cats that don't have a male partner. So the takeaway is that if we can create a bijection between two sets, they are the same size. One last thing to mention is that if a function is a bijection, then it is invertible. And likewise, if a function is invertible, then it is a bijection. In our case, instead of drawing arrows from the male cats to the female cats, if the function is a bijection, we can draw arrows from the female cats to the male cats. You can check that this inverse function is one-to-one and onto, and thus it is still a bijection. That's all fine for small numbers, but what if you had infinite singles? Can we still make a perfect matchmaking system? Buckle up, because math's about to go on the wildest speed dating spree of all time. Let's start pretty simple by labeling each of the infinite male cats with a number. The first cat would be 0, the second would be 1, the third would be 2, and so on. And we could do the same with the female cats, labeling the first female cat with 0, the second with 1, and so on. Then we can form a bijection by matching the same numbers. So male cat number 0 would be matched with female cat number 0, and male cat number 1 would be matched with female cat number 1, and so on. This is the simplest matchmaking function, which is a bijection. Everyone finds a partner, and no one is left out. Mathematically speaking, this is just the identity function, which for each input returns the same value as the output. The thing is, we can change how we label the cats to get different bijections. For example, instead of labeling the female cats going from 0, 1, 2, 3, and so on, we can label them using just even numbers, so 0, 2, 4, 6, and so on. Then to make the bijection, each male cat is paired with a female cat that has twice the value. So male cat number 0 matches with female cat number 0, and male cat number 1 matches with female cat number 2, and male cat number 2 matches with female cat number 4, and so on. You may think that this isn't a bijection since you aren't matching with odd-numbered female cats, such as female cat number 3. But really this is just a lesson in terminology. Since we are labeling all of the female cats with an even number, there are no female cats with an odd number. The set of all female cats here is just the even natural numbers, not all of the natural numbers. If it was the case where there was a female cat associated with every natural number, and we were only matching to the even numbers, then this function wouldn't be a bijection since it wouldn't be onto. It wouldn't ensure at least one x for every y. Let's consider another example similar to this one. Let's label the female cats so that each is associated with a perfect square. So the first female cat would be 0, the second would be 1, the third would be 4, the fourth would be 9, and so on. We can still form a bijection by making the matchmaking function equal to n squared. Then 0 would match to 0 squared, which is 0, 1 would match to 1 squared, which is 1, then 2 would match to 2 squared, which is 4, and so on. Like before, this is a bijection since we are considering all of the female cats to be associated with a perfect square, not a subset of the natural numbers. These last two examples may seem a bit paradoxical to you, and at first glance, you'd be right. Some numbers are even, while others are not. Therefore, all of the natural numbers, including both even and odd, must be more numerous than just the even numbers. And yet, for every number, you can double it and get a corresponding even number. Hence, the first set cannot be larger than the second. Likewise, some numbers are squares, while others are not. Therefore, all the numbers, including both squares and non-squares, must be more numerous than just the squares. And yet for every number, there is exactly one square. Hence, the first set cannot be larger than the second. In other words, intuitively, there are more natural numbers than even numbers or perfect squares, but you are able to form a bijection between the natural numbers and the even numbers, and you are able to form a bijection between the natural numbers and the perfect squares, which means that there must be an equal number. This is known as Galileo's paradox, and he wrote about it in his final scientific work known as Two New Sciences. His solution? He stated that the attributes of equal, greater, and less don't apply to infinite sets like they do to finite sets. During the 19th century, George Cantor was able to come up with a way to define comparisons among infinite sets that bypassed this restriction, which is good if we want to match an infinite number of kitties and continue with the video. In essence, he defined the comparisons as if there is a bijective function between the two sets, they are the same size, even if that messes with our intuition a bit. Let's now consider a fourth example. Imagine that you still have an infinite dating pool where the males are identified by the natural numbers as before, but now half the females identify as positive and the other half as negative. In other words, you can represent the males as the natural numbers and the females as the integers. Is a bijection still possible? Yes. Consider this function. If the male cat is even, then map it to n over 2. If it is odd instead, then map it to negative n plus 1 over 2. Using this function, 0 is even, so it would map to 0 over 2, which is 0. 1 is odd, so it would map it to negative 1 plus 1 over 2, which is negative 1. 2 is even, so it would map to 2 over 2, which is 1. 3 is odd, so it would map it to negative 3 plus 1 over 2, which is negative 2. Therefore, the overall mapping switches between positive and negative integers, but it does form a bijection, and thus the natural numbers and the integers have the same size. And it even gets crazier than that. Imagine that now each female cat decides to identify with a fraction whose numerator and denominator are relatively prime, which means that they share no common factors. This means that the female cat with the fraction 3 over 6 is the same as the cat with the fraction 1/2. If we now want to make a bijection between the natural numbers, aka the male cats, and the rational numbers, the female cats, we need to get a bit creative. Here we have a grid where I've labeled the y-axis as the numerator of the fraction and the x-axis as the denominator. We can then start at the origin and go to every point in this grid by traveling in this spiral pattern. Note that along this spiral pattern, we hit points that are invalid, such as the entire x-axis, since that would mean dividing by 0, as well as points that are duplicates of each other, such as 2 over 2 being the same as 1 over 1. So we'll remove those points. You can now hopefully see that by starting at the origin and moving around with the spiral, you can map each rational number with a natural number, and since we removed all of the duplicate rational numbers, it is a perfect matching. So just to make sure that everything is clear, we were able to match the natural numbers to the even natural numbers, the perfect squares, the integers, and the rationals. Thus, all of these sets have the same size. You can form bijections between any two of them. But unfortunately for you, there are some sets that cannot be matched. As our final example, let's consider an infinite dating pool where the males are identified by natural numbers as before, but the female cats each identify with a real number. For example, there's Pi, who is well-rounded but completely irrational, and square root of 2, whose irrationality caused quite a stir in ancient Greece, in addition to all of the other numbers we've seen so far. Now to simplify things, we'll consider just the real numbers between 0 and 1, but later I'll show how you can extend this to all real numbers. Imagine you have a list of all of the real numbers between 0 and 1 as such, where each number is associated with a natural number. And this list extends into infinity, so somewhere in this list would be the square root of 2, somewhere would be 0.3 repeated, and somewhere would just be basic fractions like 0.1, which don't repeat. The list of real numbers is special in that, paradoxically, we can always create a new real number which doesn't exist in it. We do this by making sure that this new number has a different nth decimal position than the nth element in the list. That is, it differs from the first element's first decimal point, the second element's second decimal point, the third element's third decimal point, and so on. Thus, this new number doesn't match any of the numbers in this list, and therefore can't be a part of this list. Consequently, you can't match the natural numbers to the real numbers. There are just too many of them. Recall that I didn't match the natural numbers to the real numbers, but instead only the natural numbers to the real numbers between 0 and 1. As it turns out, the set of all real numbers and the set of real numbers between 0 and 1 have the same cardinality. That is, they have the same number of elements, and you can actually form a perfect match. In this case, the matchmaking function is 1 over 1 plus e to the x. This takes in a real number and gives out a number between 0 and 1. And since this function has an inverse, this function is bijective. And in case you're wondering, the inverse function is the natural log of 1 over x minus 1, which takes in a real number between 0 and 1 and gives out a real number. So there you have it. We showed that even seemingly larger sets can still be matched with the natural numbers. The integers, despite including negatives, turned out to be no more numerous, and even the rationals, which seemed like an overwhelming mess of fractions, were countable with the right system. In the end, no matter how chaotic things looked, we found a way to match everything up, proving that they were all countably infinite. But then we met the real numbers, and everything fell apart. No matter how we tried, there were always unmatchable cats left behind. Unlike the countable sets, the real numbers formed an uncountable infinity, too vast to ever pair it perfectly. Infinity is strange. Sometimes not every cat finds a match. Maybe love, like infinity, isn't always about finding a perfect match. Sometimes it's about understanding the possibilities and embracing the mystery of what can't be paired. Thanks for watching.